We have something that's very different in a couple of ways. Number one, it's not trigonometric. Number two, it's actually a definite integral. This gives us a chance to practice our integrating. What we have is the integral from 0 to 2 of the absolute value of 2x minus 1. Here's the thing. We can't perform calculus on absolute value functions. You may recall, very early in this course, we looked at the absolute value of x, and we expressed it as a piecewise defined function. We said that it's equal to x if x is greater than or equal to 0, and it's equal to negative x if x is less than 0. And the deal here is that the piecewise defined function's domain splits at the vertex of where the vertex of the graph is. If we consider y equals the absolute value of 2x minus 1, then I still want to be able to I think visualizing is helpful. I want to be able to visualize the graph. And in order to know where the vertex is, I want to take what's inside the absolute value, set it equal to 0. So 2x minus 1 is equal to 0 implies that x is equal to 1/2. And so where x is 1/2, I know that that's where the vertex of the graph is going to be. And then the 2 in front of x tells me that this is going to have a steep slope, right? So it's got a slope of 2 instead of 1. And then likewise for the left branch of it. We can see from the picture, and we can also reason that the absolute value of 2x minus 1 is equal to 2x minus 1 if x is greater than or equal to 1/2, and the negative of 2x minus 1 if x is less than 1/2. So you can see that the value x equals 1/2 is key. Now I look at the interval over which I'm integrating. It goes from 0 to 2. It contains the number 1/2. So what I need to do is split this up into two integrals. One of them is going to go from 0 to 1/2, and the other is going to go from 1/2 to 2. The integral that goes from 0 to 1/2 is the integral over which our function is defined by the negative of the quantity 2x minus 1. So I'm going to write that as 1 minus 2x. And that's our integrand for that interval. For the interval from 1/2 to 2, it's the function is defined by 2x minus 1. And so that's my integrand, 2x minus 1 dx. And then we integrate these separately using the power rule. I'd like for you to do that and then come back when you're done. Using the power rule for integration, 1 minus 2x integrates to x minus x squared. That's going to be evaluated from 0 to 1/2. And then 2x minus 1 integrates to x squared minus x, and that's going to be evaluated from 1/2 to 2. There's a temptation to try to collect like terms, or there's a 1/2 floating around. It'll never work because this answer here has an opposite sign to this answer here. So we always will have to do these separately. Ultimately, we get an answer of 5/2. The net change theorem is a pretty straightforward theorem. It says that the integral from a to b of f prime of x dx, that would be a rate of change, is equal to f of b minus f of a. It looks like the second fundamental theorem of calculus. In order to see what it's saying, we're going to look at a couple of applications. First, we have a honeybee population starts with 100 bees and increases at a rate of n prime bees per week. So the rate is bees per week, right? That's a rate. And n prime is the derivative of the number of bees over time. The question is, what does 100 plus the integral from 0 to 15 of n prime of t dt represent? Well, let's just write it out using the net change theorem. We have 100 plus the antiderivative of n prime is going to be n, and I'm evaluating at the upper limit of 15. So 100 plus n of 15 minus n of 0. Now we started with 100 bees, and so in terms of if t is a week, right? T is in weeks. We have bees per week, so t is in weeks. Then 100 is n at 0 weeks. So this thing equals 100 plus n of 15 minus 100. And so that is equal to n of 15. Now, if n prime is bees per week, then n is the number of bees. For t equals 15, that means we're looking at 15 weeks. So it represents the number of bees after 15 weeks.